All right, so in this lesson, we are going to really focus in on what a hypothesis test is and how to run a hypothesis test. As we go through this lesson, we're also going to kind of jump back and forth between the example that we work through and the big ideas. Okay, I have not created a big idea video for this particular lesson. But we're going to incorporate the big ideas into the lesson as we go. All right? So let's jump into a hypothesis test. Here is our example. It says a teacher believes that 85% of the students in her class will want to go on a field trip to the local zoo. She performs, here we go, a hypothesis test to determine if the percentage, we're going to underline a couple of things here, to determine if the percentage is the same or different. Okay, underline same or different. She performs a hypothesis test to determine if the percentage is the same or different from 85%. The teacher samples 50 random students and 39 reply that they would want to go to the zoo. For the hypothesis test, use a 5% level of significance. So all of those things that we just underlined are important. Now, I want to focus just a little bit here on the 5% level of significance. We have seen and we have talked about 5% in the past. Can you guys remember, like, how do we use 5%, or how have we used 5% in the past when it comes to probability? I want to share with me? What do you think? What do you remember, Chloe? Statistical significance. And it's actually even a part of the name here. 5% level of significance. What we have said in the past is that if we find a probability of something, and the probability of that event is less than 5%, then we say that it is unusual. We also can say that it is statistically significant. So this level of significance that we're going to use, this is the same level of significance that we have used in the past to determine if something is unusual or if it is statistically significant. Okay? All right. Now, before I switch to the next slide here, and before we start to go through the process of this hypothesis test, I want you to know that I want to give you a little bit of an idea of what a hypothesis test is. In the world of statistics, there are times where there is a claim or a belief. So like in this particular case, the teacher believes that 85% of the students will want to go to the zoo. Well, that belief or that claim in a hypothesis test is being put on trial, okay? A hypothesis test is very similar to like a criminal trial. Somebody's committed a crime or they are accused of committing a crime, and they go and they have a trial. And I'm going to refer back to that a few times. But in a trial, there is evidence. And what you are trying to do, or what the prosecutor is trying to do, is provide enough evidence to convict that person who is being accused of the crime. It's the same thing in a hypothesis test. We are going to collect a sample, and our sample is going to be our evidence. And what we are going to determine mathematically is our sample enough evidence? Does it give us convincing evidence that this number that we are putting on trial is like, does the evidence support that number, or does the evidence not support that number? That's what we're looking to do. Okay? So a couple of different times as we go through the rest of this lesson, I am going to refer back to a trial. And I think that's a really good analogy for a hypothesis test. All right, let's jump right into now. I guess let's now jump into the hypothesis test. I'm getting a little bit of lag in my computer here. There we go. All right, so we start off with state. And what are we going to state? Well, it's in your notes, but we're going to start off by stating the first thing we are going to state is our parameter. And the parameter that we are going to be working with is, first of all, P, not P hat, but P, because it is a population proportion. And our P is going to be the true proportion of students that want to go to the zoo. There we go. P, our parameter that we are working with, is the true proportion of students that want to go to the zoo. So anytime you see the letter P, that's what it represents, the true proportion of students that want to go to the zoo. The second thing that we are going to state is our statistic. And our statistic, you don't have to write this down, but I'm going to put in parentheses, this is our evidence. Okay? Our statistic is our evidence. Well, the statistic is going to be P hat. It is a sample statistic, so it's P hat. And in this specific case, it was 39 out of 50. And 39 out of 50 is 0.78. So there is our statistic. So we've defined our parameter, we've written down our statistic, and now we need to state the level of significance. Okay, I think in your notes it says significance level. And the level of significance is given to us, but there is a symbol that goes along with it. And the symbol is alpha. It's not the best alpha. Let's try that again. No, that's not any better either. Let's try that one more time. That's good enough. Alpha kind of looks like a fish. Okay, alpha, and in this case, is equal to 0.05. Okay, our level of significance is 0.05. Now, this is a little bit of a side note. This is a little bit of bonus material here. So I'm going to change colors. This is not a part of the process, but there's something that you should know about alpha. Okay, alpha, I'll use the symbol. Alpha can be any percent, but 5% is the most common. Most of the time when you are given an FRQ and you are asked to run a hypothesis test, they're going to tell you that alpha is 0.05 or 5%. Occasionally, you will see alpha as 1% or 10%. Those are probably the three most common, 10%, 5%, 1%. But the other thing that I would say is this. If you are not given a level of significance, if it just says run a hypothesis test and doesn't give you a level of significance, just use 5%. Okay? It's what we've used in the past when we were trying to determine if something was unusual or statistically significant. So if they don't tell you the level of significance, just use 5%. Okay? All right. The last thing that we need to write down in this section of stating things is our hypotheses. Now, I'm going to write it down, but I'm also going to jump ahead to the big ideas and write some things down in there as well. So let's start off by writing down what our hypotheses would be. By the way, if you're talking about more than one hypothesis, they are called hypotheses. Okay? Well, we have two kinds of hypotheses that we are going to talk about. So I'm actually going to start over here with some bonus material. Okay? The first hypothesis that we write down is called the null hypothesis. Okay? The first hypothesis that we write down is called the null hypothesis. And the symbol for the null hypothesis is H with a little subscript 0. And I actually think that H, that's supposed to be H sub O. Okay? So the null hypothesis. The other hypothesis that we're going to look at is called the alternative hypothesis. And the symbol for the alternative hypothesis is H sub A. So a little bit of symbology there. Null hypothesis, H sub O, and alternative hypothesis, H sub A. All right, let's go back to the actual work, and let's write down our null and alternative hypotheses. For the null hypothesis, one thing that you need to remember is after you write this symbol, you need to write a colon, okay? Do not put an equal sign. It needs to be H sub O or H naught is what that's called, and then put a colon. And our null hypothesis is the thing that we are putting on trial, okay? In a hypothesis test, we are putting a number on trial. And the number that we are putting on trial in this case is P equals 85% or 0.85. Okay? The null hypothesis that is being put on trial is P equals 85% or P equals 0.85. The alternative hypothesis in this case is going to be P is not equal to 0.85. Now, you don't have to write this down. This does not have to be written when you run a hypothesis test. But one thing that I have gotten into the habit of doing is writing down a sentence or a phrase that tells me what these mean. So this right here, this null hypothesis, just basically tells me that the proportion that want to go to the zoo is truly 85%. And then down here, the proportion that want to go to the zoo, want to go to the zoo is different than 85%. Now, I see a lot of you writing that down, and that's fine, but I'm just telling you what I just wrote down in red, you do not have to write it down, okay? You do not have to write this down. I have gotten into the habit over the years of writing this down just to help me. Sometimes I don't write anything down with my null and alternative hypotheses, but if you do write something like that, just to give it a little bit of context, it's okay. but it's not required. I do not require it. AP testing does not require it. I will never take off if you don't put something like this. You might see me do it. You don't have to do it. Okay? Sometimes it's helpful for me to remember the context of things. Okay? All right, now, before we jump to the plan, I want to jump ahead to the big ideas because there's a couple of things that I want to talk to you about with, concerning the null and alternative hypotheses. So flip your papers over, and if you're watching online, we're jumping ahead to the big ideas. And I want to talk just a little bit about the null and alternative hypotheses. All right, here we go. So let's start with the null hypothesis. Well, we already talked about the symbol for the null hypothesis, and it's H sub 0 or H sub O. But the other thing about the null hypothesis that you should know is it will always have an equal sign. Okay? Always has an equal sign. It will never be anything other than equal to in the null hypothesis. Never, never, never will it be anything other than equal to. The alternative hypothesis, again, we've already seen the symbol for it, but I'll write it down again. But the alternative hypothesis can be one of three things. It can contain not equal to, less than, or greater than. It could be any one of those three things. Not equal to, less than, or greater than. Oops, can't spell greater than. Let's try that again. Greater than. Now the question comes up, how am I supposed to know which one it is? Well, the wording of the question, when you read your FRQ, the wording of the question will give it to you. If you go back to the original question, I even underlined it, but if you go back to the original question, it says the same or different. She performs a hypothesis test to determine if the percentage is the same or different. So it doesn't say she performs a test to see if it's less than. It doesn't say she performs a hypothesis test to see if it's greater than. She just wants to know if it's different than. So that's why in this specific question, our alternative hypothesis is not equal to. Okay, it's a not equal to symbol. Oops, I thought I had my, let's do that again. There we go, not equal to. All right, let's jump back to our notes. Let's jump back to the actual running of the hypothesis test. Now, if you're watching this video online, you may be getting bored right now. If you are actually sitting in class, you may be getting bored right now. And I totally understand that. But hang in there, okay? Hang in there. Today is just a good old-fashioned note-taking day, all right? It's just one of those things where you just have to watch me, listen to me talk, and write down your notes. Now, obviously, if you have questions along the way, you can ask. If you're watching online in video form and you know my email, just send me an email and I'll help you with that. All right, here we go. Let's go back to the plan because that's the next thing that we need to do. Now, this should be pretty simple. The plan for a hypothesis test is the same as the plan for a confidence interval. So we're going to start off by naming the procedure. And the name of our procedure is this. we are running a one sample Z test for P. Okay, we are running a one sample Z test for P. And that's pretty self-explanatory. We collected one sample of students. It is a test. It's not a confidence interval. It's a test. It's going to be a Z test because eventually we're going to use a Z score to find the area under the curve to find a probability. And we're running this for a proportion. So this is called a one sample Z test for P. The second thing that we need to check in the plan are our conditions. And our conditions for a one sample Z test for P are the same as our conditions for a one sample Z interval for P. And we start off with randomization. And all we have to state is the sample was collected at random. So I'll write it like this, give it a little bit of context. The teacher collected a random sample. That's all we have to say for that. We want our sample to represent the population. So as long as we collect a random sample, we're in good shape and we can make that statement. The second condition, we all should know. You guys tell me, what's the next condition we should check? 10% condition. And our sample is for 50 students. Now, I don't know how many students are at this school. I honestly don't know. They don't tell us. So this condition is actually going to be an assumption. Sometimes when we talk about the conditions, we don't just call them conditions, we call them assumptions in conditions. So we kind of have to assume that our sample size of 50 is less than 10% of the population. So I'm going to write it like this. I'm just going to write it like, let's say n equals 50 is less than 10% of all the students at the school. Now, you guys that have been, a part of this class, if you've been watching online, you know that sometimes I will put the word certainly in there. N equals 50 is certainly less than 10% of all the students at the school. I left it out this time because I'm not 100% sure on that. It's not obvious that there's at least 500 students, but we're actually turning this condition into an assumption, okay? So then we're going to get to our third condition. And our third condition, the large counts condition. So this is condition number 3. Large counts. And I don't have to put this in there, but I'm just going to put normal just as a little reminder for myself. That's why we check the large counts condition, because we want, as long as the large counts condition is satisfied, we're going to end up with a normal distribution. Now, we need to check n times p and n times 1 minus p. We do not check n times p hat. The only time we would check n times p hat and n times 1 minus p hat is if we were working with a confidence interval. And that's because we don't know what p is. But in a hypothesis test, we are assuming that we know what p is, and in this case, we're assuming that p is equal to 85%. So now we check this. So our sample size is 50. 50 times 0.85, that is equal to 42.5. Is 42.5 greater than or equal to 10? Yes, it is. So we're good there. Then we check n times 1 minus p. So this would be 50 times 0.15. And that's equal to 7.5. And is 7.5 greater than or equal to 10? Uh-oh. No, it is not. So now what do we do? Well, let me tell you. First of all, this kind of goes back to some of the questions that I've heard earlier today, and even a question I heard earlier in this class. What do we do if one of our conditions is not satisfied? What are we supposed to do? Because if it's not satisfied, I'm not really supposed to do the rest of this test. Well, here's my answer. First of all, my hope is that if I give you a question on a test, my hope is that all of the conditions will be satisfied. If I want you to go through an entire hypothesis test, or if I want you to go through an entire confidence interval, my hope is that I've done a good enough job writing the questions so that all of the conditions have been met. Same thing for the AP test. In fact, in all the years that I've been doing this, I have never run across an AP FRQ question, an FRQ that's been on the AP test, where the conditions were not satisfied. Okay? Never had that happen. But I have seen a question like this, where the question is written and one of the conditions is not satisfied on purpose. But instead of asking you to run a full hypothesis test, or instead of asking you to go through all the steps to construct a confidence interval, the question says, like it sets everything up, and then it says, would it be okay to create a confidence interval? So basically what they're asking you is, are all the conditions satisfied? And if they are, then it is okay to create a confidence interval. But if they're not, you need to recognize which one of the conditions has not been met and make a statement about that. Okay? You guys see what kind of question that could be? But I have never seen an FRQ on the AP test that wants you to do the whole thing and one of the conditions has not been satisfied. Okay? All right. Well, now we get to this. Like, I don't want to stop here. Okay? I want to keep going. But what do I do? Well, I don't remember who told me this, but somewhere a number of years ago, I was at a conference, and the conference was all about AP stats, and they were talking about how things are graded and how to teach different things. But what they told me was this, and I've used it ever since. If you ever run across a condition that is not satisfied, and you know you're supposed to just do the whole thing, what you should say is this: proceed with caution. Proceed with caution. Now, I've taught this lesson 3 times today. And every time I've brought this up and said proceed with caution, I've heard at least one person in the room chuckle. Okay? And that's okay. When I heard it the first time, I kind of did the same thing. I was like, really? That's what we're supposed to do? You know, and if you're watching online in video form, I wouldn't be surprised if you looked at it like, really? Are you serious? But yes, that's what we as AP Stats teachers have been taught. If you ever come across a condition that is not satisfied on a test question, then just say, we will proceed with caution, and then keep going. Okay? But like I said, I've never seen it. Okay? I can't remember ever seeing it. All right, so let's continue. We looked at stating, and we stated our parameter, we stated our level of significance, we stated our null and alternative hypotheses, we stated our statistic. Then we've gone through the plan, and here in the plan, we have named our procedure, and we have checked all three of our conditions. All right, let's go to the do. And there's a number of different things that we need to do with the do. But the first thing we're going to do is write our general formula. So we're going to write down our general formula. And we are at the point where we are ready to find the area under the curve. And so our general formula is for a z-score. And our general formula for the z-score is our statistic minus the parameter divided by the standard deviation. We're going to take our statistic minus the parameter divided by the standard deviation. You guys have been using z-score formulas since all the way back in the middle of first semester. Sometimes we've written it like this: value, don't write this down, but value minus the mean divided by standard deviation. But they all follow this same, generalized formula. In this case, it's a statistic minus the parameter divided by the standard deviation. All right, now let's write down our specific formula. And our specific formula is z equals p hat, which is our statistic, minus p, which is our parameter, divided by the standard deviation, which for this sampling distribution is p times 1 minus p over n, or I should say the square root of p times 1 minus p over n. We've seen this before. We used this formula to find the area under the curve for a sampling distribution for proportions. And so we're going to use it again. Now we can go ahead and do our work. Now, when we do our work, what we are trying to find is something called the test statistic. I can't remember if I wrote that in your notes, if I typed that on your note sheet, but I want you to write that down. We are about to find something called the test statistic, and the test statistic is our z-score. So we're going to plug in the numbers and find our test statistic right now. So this would be, let's see, p hat was 0.78 minus p, which was 0.85. That's in our null hypothesis, divided by the square root of p times 1 minus p over n. So 0.85 in this case, 0.85 times 0.15 divided by 50. If you don't have your calculator handy, you might as well get your calculator out. If you're watching online and you don't have your calculator handy, you probably want to grab that as well. And we're going to go ahead and calculate this. This is our z-score. This z-score is called our test statistic. And in this case, our test statistic is negative 1.39. Okay, I rounded off the 2 decimal places. My hope is that you guys are getting the same value, negative 1.39. All right, once we've found our test statistic, the next thing that we want to find is something called the p-value. P-value. In order to find the p-value, I'm just going to find the area under the curve. You guys have been doing this once again since the middle of first semester. So I'm going to draw this picture. Mr. Mays, do we have to draw the picture? Yes. That's why I told you to draw the picture so long ago, because I knew you would have to draw it again here. So we're going to draw our picture. This is a normal model with a mean of 0 and a standard deviation of 1. And our z-score, our test statistic, is negative 1.39. And I'm going to find the area under the curve just like that. I'm going to draw that picture. Okay? But before you go grabbing your calculator and going normal CDF from negative 99 to negative 1.39 and then 0, 1, before you do that, we need to jump ahead to the big ideas. Because there's some things about the p-value that you need to know. There's some things about hypothesis tests that you need to know. So flip your note sheet to the big ideas. I'm going to skip ahead to the next slide, get a blank slide here. And I want you to write this down in your big ideas. Here we go. There are 3 types of tests, hypothesis tests. There are two-tailed tests. There are left-tailed tests. And you can probably figure out the last one. There are right-tailed tests. So two-tailed tests, left-tailed test, right-tailed test. Now I'm going to draw a picture for each one of these. A two-tailed test means that when you find your area under the curve, you're going to find the area for both tails, okay? Just like that. And the z-score on the left, the test statistic on the left, is going to be the same as the test statistic on the right, except one will be negative and one will be positive. So in order to find your p-value, in fact, let me draw this as well, the area under the curve right here for a two-tailed test is the area in both tails. Okay, the area in both tails. For a left-tailed test, it's just like it sounds. It's a test where you only find the area in the left tail. And for a right-tailed test, it's just like it sounds. You only have to find the area in the right tail. Now, I kind of got ahead of myself just a little bit, so I'm going to do a little bit of erasing here and then come back to this. How do I know if I'm going to run a two-tailed test, a left-tailed test, or a right-tailed test? Well, you will know what type of test to run based on the symbol in your alternative hypothesis. If the symbol in the alternative hypothesis is a not equal to sign, then you are running a two-tailed test. If the symbol in your alternative hypothesis is a less than sign, then you are running a left-tailed test. And if the symbol in your alternative hypothesis is greater than, then you are running a right-tailed test. And in each one of these, the area under the curve is your p-value. So for a left-tailed test and a right-tailed test, the p-value is just the area in that one appropriate tail. But for a two-tailed test, you're going to find the area in one of the two tails and then double it. Okay? You're going to find the area in one of the two tails and then double it. One last thing that I will say before I go back to the question is, because this question comes up, how do I know what the symbol should be in my alternative hypothesis? How do I know if it should be not equal to, less than, or greater than? Well, you just have to read the question. Okay, and I'm not trying to be sarcastic there, but somewhere in the question, it will say less than or fewer than or something like that, and that will tip you off that it is a left-tailed test. Or it'll say greater than or more than, and that will tip you off that it is a right-tailed test. In our case, it's a two-tailed test because the original question says the teacher wants to run a hypothesis test to see if there is a difference. No, not that. To see if it's different than 85%. Okay? If it's different than, that means she doesn't know if it's less than or greater than. She just wants to test to see if it's different than. So that's why it's a two-tailed test, not equal to. All right, let's go back and now find our p-value. So in order to find our p-value for a two-tailed test, I'm going to put this. Now, you always need to label your p-value, okay? In other words, you need to say the p-value equals whatever it ends up equaling, okay? So you don't have to write the calculator notation. I'll write this in green because it's not necessary. But I'm going to go 2 times normal CDF, and I'm going to go from negative 99 to negative 1.39 with a mean of 0 and a standard deviation of 1. And if you do this calculation right here, 2 times the area under the curve, normal CDF for all of that, you end up with 0.165, 16.5%. So the one tail by itself, I forgot to do something here. This is a two-tailed test. So I need to draw and shade in both tails. So I don't want to forget to shade both tails. It's a two-tailed test, and my p-value ends up being 0.165, or 16.5%. All right. If this was a left-tailed test or a right-tailed test, I wouldn't have to multiply the tail times 2. Okay? All right. Well, what does the p-value tell me? I've done all of this. I've gone through the process. I'm pretty familiar with, finding a z-score and then using that as my test statistic and finding the area under the curve. But what is this p-value telling us? Well, let's kind of discuss it just a little bit. A p-value of 0.165, 16.5%. Is that statistically significant? As I stand in front of my students, a bunch of you are shaking your head no. And if you're watching online, hopefully you're also saying no. Why is it not statistically significant? Because it's not less than, in this case, 5%. It's not unusual. So let's go back to like a trial. This hypothesis test is putting the parameter of 85% on trial. When we get to this p-value, what we're saying is 16, let me start that sentence over. The probability of getting this sample is not unusual. There's a 16.5% chance that this teacher is going to get 39 out of 50. That's not unusual. So therefore, that 85% that I thought was true, yeah, I still am okay with it. I have no problem with that 85%. So how do we use that and draw our conclusions? That's what we're going to do next. All right, let's write our conclusion. So what does our conclusion look like? Conclude. This is what I want you to write down. And I'm going to write it, and then I'm going to unpack it for you. Okay, so just trust me on this. Write it down, and then I'll unpack what it means. And we're going to write it like this. Since the p-value is greater than alpha, and I'll go ahead and put alpha equals 0.05. Since the p-value is greater than alpha, let's say we, because it's the teacher, we will fail to reject the null hypothesis. Okay, I'm going to underline fail to reject. You don't have to underline it in your answer, but I'm going to come back to that. Since the p-value is greater than alpha, we will fail to reject the null hypothesis. There is not enough evidence to support the alternative hypothesis, which says the proportion of students that want to go to the zoo is different than 85%. Woo! That's a lot to write down. Do we have to write all that down, Mr. Mason, to get full credit? Yeah, you do. You do for me, and you do for the AP test as well. But let me unpack this a little bit for you. When you get to the end of a hypothesis test, you need to talk about the null hypothesis and what you're going to do with the null hypothesis. And you also need to talk about what you can do with the alternative hypothesis. The third thing that needs to be a part of your conclusion is context. Okay, we've talked all year long about how important it is to write answers in context. So we're going to talk about what happens to the null, what happens to the alternative, and we're going to write it in context. Okay, just a couple more minutes. If you're watching this video online, hang in there. If you're in class, don't fall asleep on me. We're getting close. All right. I'm going to jump ahead and do a little bit more big idea stuff. Okay? So this is a little bit more big idea stuff. And by the way, there is no big idea video for this lesson because I'm doing all the big idea videos in the lesson, or I'm doing all the big ideas in the lesson itself. So here we go. So here's what we've got. We need to, in our conclusion, we need to write something about the null hypothesis, and we need to write something about the alternative hypothesis. Well, there's two things that we can do with the null hypothesis. And those two things are we can reject it or fail to reject it. So I'm going to write those down. We can reject the null hypothesis, or we are going to fail to reject the null hypothesis. And those are the two things that we should say, one or the other. Now, when do we reject and when do we fail to reject? So I'm going to change colors here. And our decision about the null is based on the p-value. If the p-value is less than alpha. If the p-value is less than alpha, that means that our sample is statistically significant, and that means that our null hypothesis might not be true, so I'm going to reject it. If the p-value is less than alpha, I reject the null hypothesis. And then consequently, if the p-value is greater than alpha, then I am going to fail to reject the null hypothesis. And really, this is our evidence, okay? If our p-value is really, really small, that means that our evidence tells us to reject the null hypothesis. If our p-value is not less than alpha, if it's greater than alpha, then we do not have enough evidence to reject the null hypothesis, so we say fail to reject. There's a word that you want to avoid, and that word is accept. A-C-C-E-P-T. Accept. Yes, we can say we reject the null hypothesis, but we don't want to say we accept the null hypothesis. We want to say fail to reject. Let's relate it back to a trial. At the end of a trial, the judge turns to the jury and says, "Ladies and gentlemen of the jury, have you reached a verdict?" And the head juror stands up or says to the judge, "Yes, Your Honor, we have reached a verdict." And they stand up and they say, "We, the jury, find the defendant." And what are the two things? What are one of the two things that they will say? "We, the jury, find the defendant guilty or not guilty." What's the word that they don't say? Innocent. Okay? In a trial, the person who is on trial does not have to prove that they are innocent. There is either going to be enough evidence to say that they are guilty, or there is not enough evidence to say that they are guilty. And so that's why at the end of a trial they say guilty or not guilty. Okay? It's the same way with a hypothesis test. We either have enough evidence to reject the null hypothesis, or we don't have enough evidence to reject the null hypothesis, and we would say fail to reject. Okay? So that's what it comes down to. You don't want to use the word accept. You either reject the null or you fail to reject the null. What about the alternative? Well, what you do with the alternative depends on what you did, what your evidence tells you. So if I end up rejecting the null hypothesis because the p-value is statistically significant, what we see about the alternative is this. We say that there is enough evidence does support. Okay? We say we do have enough evidence to support the alternative hypothesis. But if we fail to reject the null, meaning we don't have enough evidence to reject the null, then in this case we do not have enough evidence to support the alternative hypothesis. So if we end up rejecting the null, that means that the evidence does support the alternative. But if our evidence supports the null, and or I should say we don't have enough evidence to reject the null, then we also don't have enough evidence to support the alternative. You can't support both, and you can't be against both. If you reject one, your evidence supports the other. If you fail to reject the null, then you don't have enough evidence to support the alternative. Okay? There's just one more thing that I want you to write down, and that is our definition for p-value. Okay? Knowing the definition of the p-value is something that you need to know, because I can guarantee you that at some point in time, you will have a question that asks you to explain what the p-value means. And it means this. The p-value is the probability of getting your sample assuming the null hypothesis is true. The p-value is the probability of getting the sample that you got, assuming that the null hypothesis is true. So in our case, what is the probability that that teacher gets a sample of 39 out of 50? Well, assuming that 85% of the students truly want to go to the zoo, there's a 16.5% chance that she will get that sample that she got. And that's not unusual, and therefore, I do not reject the null hypothesis, and I don't have enough evidence to support the alternative, which says it's different than 85%. Okay? All of these numbers connect together in context. Whew, that's a lot in this one lesson. This is probably one of the longest lessons that we've had. And if you're watching online and you've stuck with it for the full time, congratulations. We've come to the end. So hopefully this helps you understand a little bit more about hypothesis testing, and hopefully you have a great day.